3.4, velocity and other rates of change. So instantaneous rate of change, which we've been seeing a little bit here and there, of f with respect to x at a is the derivative f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h, provided the limit exists. So, for example, find the rate of change of an area A of a circle with respect to radius r. So, what's the area of a circle?
2 pi r?
Nope. Pi r squared.
Dang it.
Circumference, which you're going to need later also. So remember, area is always something squared, so that's how you can remember that it's pi r squared. So now I want the derivative of a with respect to r. So dA dr would be what? Josh?
It would be 0.
What did you just say?
Yeah,
Oh,
what
2
did
pi
you-
r.
Yeah. Because pi's a number, so you...
Yeah. Yeah.
But r is a variable.
Yeah.
So now that we have that, evaluate the rate of change of A at r is equal to 5 and r is equal to 10. So we just plug in 5 and then 10. So 2 pi times 5 would be 10 pi. 2 pi times 10 would be 20 pi. And then if r is measured in inches and a is measured in square inches, what units would we have for dA dr? Random thought of the day, I just realized on Yoda over there you can see his toes.
Huh?
You can see his toes sticking out.
Hayden really wants to see those toes.
No, I'm just confused. Oh! Wait, it's like one toe.
It's like a big toe sticking out.
It's one toe.
That's nasty.
It's like squirrel. I looked up and I was like, why do I see a toe?
It looks like a human big
Y'all
toe,
really
but
wanna see
green.
those
I don't like
toes?
it. I just wanted to... I don't like it. I I just want to see it.
I'm just trying to take a.
Minor
Yeah.
distract.
Take a gamble.
What are you doing? Checking to see if they're like stuck to it?
Not modern art, Christian. That's
It's like
weird.
modern art. Toes are like modern art.
That's crazy.
I don't know how.
That's so.
Well, I don't like either, so.
You don't like modern art?
Have you seen how abstract it gets?
I love it. Of course you do. I could splatter paint on a
I went
canvas
to a
and it's
museum
for
and
like
this barbed
5,000.
wire on a wall, and that was the art piece.
No way.
Because it represents their feelings.
It represents the pain of war, I think. That's what they said.
Oh.
I don't know. They
All right.
summed it up.
What units would this have?
Square inches. No? Yeah, okay. Next one.
Well, if area is square inches and R is inches,
Cute inches.
how about square inches per inch,
I don't like
I
that.
was on the right track.
which would be equal to what?
It's just
I need to write.
squared.
What is this equal to?
Inches squared. Wait, oh, I mean inches.
Inches.
Gosh.
It's the algebra that kills us.
Let's just.
Jack will just kind of like.
It's
Just took it out of us.
It's because me and Riley are going through a rough patch right now.
I know.
Is.
Oh yeah, wait. Nate, yeah, Nathan, didn't you hear Riley and Josh are dating?
Did you hear? That was funny.
Riley.
Riley called a ball in, so therefore they're dating.
Yeah.
He
He
was like in the microphone.
Yeah,
Like,
in front of the whole school.
No.
He was like.
He was
yeah.
like, it's because he's her boyfriend.
In the microphone.
Yeah.
Me and Riley both had the same exact reaction.
They're like,
I think the entire
The guy. Bob.
Bob, the Bob.
I think Mason said it.
Yeah, it was
Wait,
funny.
Mason said
Yeah,
W Riz.
They all
Yeah.
said it.
W Riz.
It was great.
Just all like one.
No, and then Holly, when I sat back down, Holly was like, "You're mine, not Riley."
I told Riley, I was like, well, maybe it's a junior senior date for you.
Oh my goodness.
She was like, yeah, he was like, I don't hate you or anything, but I don't like you like that.
You said that, Josh?
Yeah.
Hey, you just reject
Oh.
breaking hearts.
It's okay, it happens.
Yeah, what did I miss? Because I was in the office, right?
That's a lot, honestly.
Yeah.
A lot. There's a lot that happened in that, like, 2 hours or whatever.
Yeah, hour and a half, whatever it was. We didn't start 9:15.
I got called out by the guy.
Yeah.
Yeah.
He was like, I'm gonna serve to you. And I was like, okay.
The psychos.
Yeah, the psycho serve.
Is it fee different than a normal serve?
I don't know. It
I thought it was
pretty-
easier than the normal
Yeah,
one,
It
but.
was kind of easy.
I was like, it's going slower.
I really think that's the only like his serves are really what makes him win all those games. I really think.
Oh, 100%. And the rule that you have to hit it twice on your side before you're allowed to send it over.
No,
Yeah,
he would
he
not
made-
win otherwise.
But he, yeah, I was gonna say he didn't have to do that though.
Wait, he played by himself.
Yeah,
Yeah, that's his whole deal.
that's his whole like livelihood. Wait, maybe not. Does he get paid to do that?
He gets like a speaker fee. They said he did that for an all-nighter one night and played 13 games with kids and then gave a message at like 4 a.m.
That sounds.
I was like, he has a lot of energy. I don't have that much
Yeah,
energy.
he was 67. Oh,
Like, I can play volleyball for a long time, but like, honestly, my shoulder's pretty sore after yesterday.
I bet.
Mm.
Serving at us all that time.
I just need passing to be like it was yesterday.
It was good yesterday.
It was. It was actually
Because
very
if
good.
we shanked it, we had to sprint.
So passing
Like,
was
each
good.
team
I think I'm
should
just
get
gonna have my
one
clipboard and
touch.
tally every time we have a bad pass, and then we'll
Yeah.
run at the next practice. I think that'll be a motivation.
Definitely.
Yeah, that's easier for you to say, Josh. You don't have to participate in that.
I'll participate if you want to.
I do.
Do it in honor.
All right, so motion along the line. This is,
T
huh?
plus T, do.
I wrote it down, but now I have to like think about what it said.
T to T plus delta T. So position S with T as a function of time displacement over time interval T to T plus delta T. So this equation is going to look like delta S is equal to F of T plus delta T minus F of T. So average velocity, oh, we've heard that before,
Yeah.
is displacement over time, which is delta S over delta T, also known as F of T plus delta T minus F of T, all over T. This one you may not like the calculus version as much as you like the regular one.
Yeah.
Because this formula isn't hard, is it? This seems more complicated.
So that's average velocity. Instantaneous velocity is the derivative of the position function S equals F of T with respect to time. So what does this mean? Basically, if you're given a position function, all you need to do is take the derivative and you have velocity.
Okay. We only have instantaneous.
Which is often what you're looking for. The other formula is for average, so. So V of t is equal to ds dt is equal to the limit as delta t approaches 0, and this is the long way to do this, but f of t plus delta t minus f of t all over delta t. So in a sense, it's kind of like basically finding it at a point. If you're given a point, then you just plug it in for velocity. Now speed is the something of velocity. What do we know the difference between velocity and speed?
Velocity has
Speed
direction.
does not have direction.
Okay, and how do we normally represent that direction?
What? Oh, like north?
Yes, but not what I'm looking for.
Oh,
Like this, like-
yeah.
How do I know
Negative or
something's going
positive?
left by looking, yes, negative or positive. So speed is the absolute value of velocity
Okay, this has to be.
because it doesn't have direction. So speed is equal to the absolute value of v of t is equal to the absolute value of ds dt. So if we were given the position function, we can take the derivative and take the absolute value of it, and we would have speed. Then acceleration is the derivative of velocity with respect to time. Now, the other thing that you can know is that acceleration is the second derivative of position. Okay, so it's the first derivative of velocity, the second derivative of position. So if you're given position and you want acceleration, take the derivative, that gives you velocity. Take it again, that gives you acceleration. So a of t is equal to dv dt, or it's equal to d2s dt2, which just means the second derivative. And with these, I don't typically write like the y double prime like I was doing for second derivative, because I want to specify what I took the derivative of. All right, and then the last thing for notes on this, which I think is good because I think we get out at 39. Not really sure. Free fall acceleration, free fall constants. So you should already know one of them.
Gravity.
Well, that is the constant, but we're going to have it in English units and metric units. So in English units, okay, meaning the crazy system that we use that's like, feet and inches and all that. G is equal to, which is again acceleration due to gravity, 32 feet per second. Or I guess I should say second squared. S is equal to 1/2 32 t squared. And how did I get to this? How do I get from here to here to get the acceleration? Take the derivative first, so that gives me 32t. Take the derivative again, that gives me 32, which gets me to that. So this is the position function that gets me to the acceleration over here. Okay, just so you have it for reference. And this is equal to 16 t squared. And this is assuming that S, which is position, is in feet. And then in metric, which is what we've been doing in physics class, G is equal to 9.81 meters per second squared. The position function for that is S is equal to 1/2 times 9. Now, your book is going to use 9.8 instead of 9.81, just because for some reason that's what they like to use, but just to keep consistency with physics so you don't get confused, let's do 9.81, and then t squared is equal to, and I'm just going to round it, 4.9 t squared, and this is for S in meters. Something I need to remind y'all or show y'all in physics, but we can actually, so like let's say hypothetically, now at this point you probably know 9.81, we've used it enough, but we actually can store that in our calculator. So if y'all remind me when we get to physics, will we even be in physics? Yeah, we will, because we're not leaving early anymore. I'll show you how to store that in your calculator so that you can just use it going forward. You just have to hit the button and it's there for you.
So what happened with the